Hello, this is AP Physics C Mechanics, practice FRQ Set 7, question 4. A non-linear spring is compressed various distances x, and the force F required to compress it is measured for each distance. Here's the data. Assume that the magnitude of force applied by the spring is of the form Fx equals ax squared. Part A, which quantities should be graphed in order to yield a straight line, whose slope could be used to calculate a numerical value for A. So, in order to find slope, you have to use y over x, y-axis over x-axis, and we could do that by dividing x squared to the other side to get a equals f over x squared. So f will be our y-axis and x squared will be our x-axis to yield a straight line. Therefore, the quantities should be f as the y and x squared as the x. Part B, calculate values for any of the quantities identified in Part A that are not given the data and record these values in the table above. So x squared, units would be m squared, because you're squaring. And we're just basically squaring all of these values and putting it here. This would be 0.0025, 0.01, 0.4, 0.0625. Okay, part C, using the grid below, plot the quantities you list indicated in part A. Label the axes with the variables and appropriate numbers to indicate the scale. So this will be f on top, n, and this would be x squared, m squared. So now I'm going to graph these. So the scale, I'll go by 2s, go 0.01, 0.02, 0.03, 0.04, 0.05, and 0.06, 0.07. And for the F, I will go 20, 40, 60, 80, 100. Okay, next I'll graph these based on the information above. Okay. This would be around here. F is 4. At 0.1, F is 17 around here. When F is 0.225, this is 0. Okay, around here. 38. Next, 0.4, 0.04, I mean, and 68. And lastly, 0.0625 and 106. Right here. And as you see, this pretty much creates a straight line. I'll try to make the best line I can, like that. It's close enough. And that's part C. Part D. Using your graph, calculate A. So, A equals, as I said before, F over x squared. So we're going to use a simple data point, which is the second line here. F equals 17 and x squared equals 0.01 squared. And just 0.01 because that's already x squared. And you will get 1700 newtons over meters squared as our A. Okay, part E. Calculate the work done by the cart in compressing the spring 0.1 meters from its equilibrium length. Okay, so work equals f of x with respect to x, and our bounds will be, it compresses the spring 0.1 meters, and it starts from equilibrium, so 0 x. So if you go from 0 meters to 0.1 meters. And f of x equals ax squared, right here. 0.1, ax squared, and a, as we found out in part D, is 1700, x squared dx. If you integrate that, you would get 1700 x3 to the 3 with bounds of 0.1 and 0, which will get you 0.57 joules. That's part E. And part F, lastly, is calculate the speed of the car just before it strikes the spring. So, what I'm going to do is, so work equals change in kinetic energy. Our work is 0.57. And I'm going to go from when the block hits the maximum compression of the spring as our final or initial, and it will bounce back to just before it touches the spring. So I'm going to go backwards. So change in kinetic energy is KF minus KI. So KI is when it's maximally compressed. So I'll cross it out. And we're left with 0.57 equals KEF. Equals 1 mvf squared. Our m is 0.5 because it's a 0.5 mass car. I forgot to read this, but that's okay. So m equals 0.5 vf squared. 57 equals 1/4 vf squared. And then I'll move this here. Multiply both sides by 4, and you get 2.28 equals vf squared, and vf equals 1.51 meters per second. And that is everything for question number 4. I'll see you in question 5.